Hello everyone to my talk, Performance Tricks I Learned from Contributing to the Azure.NET SDK. I consider myself a practical learner, and I found the Azure.NET SDK repository the perfect spot to learn and apply interesting performance optimization techniques. What does it even mean to be a practical learner? Why? Well, I have invented that term essentially, and I'm not sure if it's even an official term, but what I usually do is when I read a book, for example, about performance optimization techniques or something else in the software industry, I feel like, I got it figured out and I can directly apply it. But once I'm sitting in front of my computer, I'm like, how does this work again? I need to like reopen the page, read it, and then I go through a series of trial and error in order to actually apply these techniques that I've read about and then actually embrace it fully. And I have done that in the Azure.NET SDK repository. And over the years, I have contributed over 70 pull requests over the years to the Azure.NET SDK. And some of them got accepted and some of them didn't get accepted. But I guess that's part of the game. And as a matter of fact, after one of these talks, someone actually also submitted a pull request against the ABP framework. And I have also been sort of a reviewer on one of these pull requests to squeeze out performance out of the ABP framework as a little side note. And in this talk, what I'm going to do is I'm going to summarize the key learnings of my adventures into the Azure.NET SDK repository in terms of performance so that you can have a head start should you wish to start applying performance optimization techniques in your code bases as well. First of all, I want to get a few details straight. So this talk is not going to be about horizontal or vertical scaling. These are techniques that are also applicable. I'm going to focus on optimization techniques that can be purely done in .NET code as well. So I'm also not going to talk about tools like benchmark.net or memory and tracing profiles, because that would be a whole other talk in of it itself, and the time is unfortunately not enough. So really the focus is, again, on performance optimizations that you can do in your code, in your C# and .NET code. My examples will be in C# .NET. Some of these examples can also be applied, or most of them can also be applied to other languages like F#, VB.NET and whatnot. Sometimes maybe some of the details may differ, but I'm going to use the samples in C# .NET because that's the primary language that I use day to day. That's where my knowledge is. So I want to present it in that way. And sometimes I also hear like, well, why would you even do stuff with .NET? Why wouldn't you basically use C and C++? Isn't that the better way to do things when it's like really performance critical? Well, as a matter of fact, I think the .NET platform itself has been evolving over the years to become a modern and high performance platform. And I think that C++ is less and less needed to achieve code that performs well at scale. And as a good example is recently the .NET team essentially ported the thread pool that was partially in managed land, partially in unmanaged land, fully into managed land, and the performance was better in some cases and on par in some other cases, but definitely not worse. And I think it's great when you can actually, when the .NET team can align essentially their code bases to do everything, as an example in C# where it's necessary because it becomes more maintainable, and we also benefit from that because then the platform is also more evolvable. So I want to stress that I think .NET is a perfect tool to actually use in also high-performing environments, and there are also plenty of industry examples available should you be interested. And then sometimes when I do these types of performance optimizations, I hear stuff like, wow, that's crazy. Is the complexity of this change really worth it? Isn't it premature optimization? And I must say, some of the optimizations that I'm going to show you here today can sometimes be called esoteric. So don't jump to conclusions and apply them blindly everywhere in the code base. Because I know it, that performance improvements can be highly addicted, but nobody likes to optimize code that is fast enough or only executed once a day, right? So these types of optimization techniques that I'm going to show you today, they have a specific purpose in a specific context where they should be applied. In some contexts, it doesn't make any sense to apply them. And that's really important, because if you're not taking the context into account, and I'm going to stress that several times over the talk, then you might be essentially your employer's time, your customer's time, and your own time as well. And sometimes these techniques and also the measuring of it can be really time-consuming activities. So you have to be mindful about that. So the important part is code has to be executed at scale. Only then these performance optimization techniques really matter. And so what it means, the code that is more efficient in the resource usage, execution time, throughput, and memory usage, then these performance optimization techniques can be applied to make it even more efficient in the resource usage, memory usage, execution time, throughput, and so on. But what does at scale really mean? So David Fowler, he's a well-known figure in the .NET space, has this pretty cool talk. I can highly recommend it. It's called "At Scale, Implementation Details Matter." And in there, he has this quote: "Scale for an application can mean the number of users that will concurrently connect to the application at any given time, the amount of input to process, or the number of times data needs to be processed." And for me, the last part is the most important part here in this quote. For us as engineers, it means we have to know what to ignore and knowing what to pay close attention to, right? So when we are new in a team, or even already sort of been there for a while, it's still possible that there are things that we don't know, right? And we rediscover our code base. And sometimes for me, even stuff that I wrote three months ago, I don't remember what I did there, and then I have to go back. But what I always do is I always try to discover the assumptions that have accumulated over time in a specific code base. And I always assume that people that have been contributing to this code base, they were smart, right? They made trade-offs, and sometimes those trade-offs involve time, pressure, delivery, some other environmental, so organizational constraints. And we have to understand those assumptions and trade-offs in order to be able to find out how is this code executed, what does it do? So what we have to do is we have to pay close attention to what is instantiated, parsed, processed, etc. For example, per request, right? Is the code executed 100 times a second, 1,000 times a second, or only once a day? That is really, really important. And then we have to basically connect to whether the assumptions that have been made in this code base affect the performance characteristics, for example, memory, throughput at scale, right? And once we know these assumptions and whether a code is executed at scale and how many times it's executed at scale, what is at play and how these assumptions play into it, we then can start optimizing the code if a code is executed at scale. If it's not executed at scale, then we don't even have to bother about these techniques, and we might find other places in our code base where we can apply these optimizations. And as a developer, I usually like to have sort of rules that I can apply, and I have brought you the most important rules today for my talk. And these are the two ones. So avoid excessive allocations to reduce the GC overhead. And the second one is avoid unnecessary copying of memory. So these are basically the two high-level categories. And if you memorize those two rules, you are going to be fine, or at least you're going to be fine in the majority of the time. Because if you take them into account, and if you look in your code bases for these things in the code that is executed at scale, you will have tremendous throughput gains over the time you're doing these types of optimizations. Let's dive head first into the first category: avoid excessive allocations to reduce the GC overhead. And the first rule there is think at least twice before using link or unnecessary enumeration on the hot path. Don't get me wrong, link is great, and I wouldn't want to miss it at all. Yet on the hot path, it's far too easy to get into troubles with link because it can cause hidden allocations, and it's very difficult for the JIT to optimize it. So let's have a look at a piece of the code from the AMQP receiver. The AMQP receiver is the driver behind Azure Service Bus and Azure Event Hubs for the message and event receival acknowledgement mechanics. I have here a highly simplified piece of the actual code. I also removed a few boilerplate things and replaced a few things so that's easier digestible. So what we can see here, here's this AMQP receiver. And the Azure SDK team has a few rules. So for example, one of the rules is whenever they take in a collection type from the outside, they need to take the broadest applicable enumeration type. So in our case, when we deal with lists and arrays and whatnot, we're going to be using IEnumerable. And if we zoom in, what this code has here, it has this complete internal method async, which accepts an IEnumerable string. It's called lock tokens. For you, as a sort of simplified thing, lock tokens are basically GUIDs. So a lock token represents whenever you have something from Azure Service Bus as an example, and you process it, once you're completed, you essentially acknowledge the message that you process with that lock token. And then, as I said, we're getting this IEnumerable of strings from the outside that represent these lock tokens. And what the code did then, it essentially did a lock token select, turned it into GUID, and then called toArray on it. And then the next thing, what it did, it looked into a sort of internal data structure, here represented by concurrent back, and it asked whether the lock token has already been seen in there, and if it was true, then it went on one code path, and otherwise it went on the other code path. So if we want to know what's going on, we have to decompile this code. So let's look at the decompiled version of this code. And I know this is probably a little bit overwhelming. Don't worry, I'm going to zoom in the various important parts while I'm explaining stuff. But it's a lot of gibberish code, I confess. So let's have a look. So when this code gets essentially lowered to the lower levels, when we decompile it, this is how it looks like. So the first thing that we see is, we see here this C.9__2_0 type of pattern. What this means is we are essentially in the safe land, right? Because essentially the compiler generated code that assigns a delegate to a static field. That's what we see here. So whenever we see this type of pattern, then we don't really have to worry about it because it's already a quite optimized piece of code in terms of allocations. But if you look closer, we can see on the next line, we have this new func of GUID of bool that points to a method. So essentially every time we execute this code, and this code is executed at scale because we might be receiving hundreds and thousands of messages from Azure Service Bus, and we're then completing them concurrently at scale in that specific rate, we're going to allocate a new function of GUID of bool every time we call this method. And this is totally unnecessary. So how can we optimize this? Well, we can simply turn the any call that caused this allocation into a loop. This is how it looks like. So what we're going to do is we're going to do a simple for each, and inside that for each, we're then going to check all the log token GUIDs, and if it's contained in our internal collection, whatever, then we return on one code path, otherwise we go on to the other code path. So instead of doing a link any, we're using now a for each loop with an if statement. Pretty simple code optimization, right? Okay, let's have a look what's happening right now. So if we decompile this code, if we're going to the lower code, then what we can see is now this code has changed, and we now have our beloved pattern of this C.9__2_0 whatever, right? So again, what that means, I'm going to repeat it, we have now a statically cached delegate, and the allocation that we previously had is now gone, and we don't have to worry about this anymore. So that's awesome, right? So by doing a simple change, we're now getting rid of the allocation. But why would that matter, or how does it actually impact what we're doing? Well, let's have a closer look. And in order to know, what we have to do is we actually have to measure what's going on, right? So whenever you're making changes, you need to actually, unless you're extremely experienced, but even if you're extremely experienced, I always force myself to essentially go through these benchmarks, because otherwise you might be making assumption and things are actually going in the completely opposite direction. So let's have a look. So if I ran a benchmark against different collection sizes, because we're getting IEnumerable, right? And if what we can see here, and by the way, don't worry, whenever I'm showing benchmarks, I'm showing these large print screens, but you don't have to read it all. I'm going to summarize it for you. So essentially what we can see here, and the first line is the throughput. By getting rid of the link any, we got a throughput improvement of 20 to 40%, and we got a Gen 0, that's the trash can icon, a Gen 0 garbage collection reduction by 20 to 40%, right? So that's amazing. Essentially, we managed to double the throughput of this code by just removing the link any. But those who are still awake and are closely listening to me and have seen the other code would be saying, but hold on, Daniel, you still have a link statement in there. We still have a select and to array. Could we get rid of this? It's like, yes, absolutely you can. And I have a few rules for you that I'm going to present here. In the interest of time, because I have 45 minutes-ish today, I'm not going to cover them all, so I'm just going to handpick a few. If you're interested to hear more about these rules and also before and after type of example, I have a longer version of this talk that I can happily share with you as a recording, and then you can see how I go even into more details. But let me pick a few. So the first one is when you want to essentially go from link to collection-based operations, so also getting rid of the select and to array in the previous example, what you should be doing is whenever you represent empty arrays, use array.empty. One other rule that is potentially a little bit counterintuitive, because I know that a lot of people like to use read-only connection, enumerable and whatnot. Use the concrete collection types. For performance-sensitive code that is executed at scale, when you use the concrete collection types, a lot of the scenarios where, for example, the enumerator gets boxed and then you get additional allocations, they're gone. The cheat can highly optimize that. So that's always a good practice. And for example, what's also pretty interesting is with the newer versions of .NET, there is this enumerable try get non-enumerated count. What it allows you to do, instead of using the link count method, you can actually use this method to ask a collection what the count is, and it doesn't enumerate. So you're not going to pay the price of essentially going through every element to count it like you do when you use link count. Okay. As I said, in the interest of time, I'm going to show you just the before and after, in the sense of when I get rid of all the link in the previous code, then what we're getting is, and again, I execute the benchmark and I'm doing a comparison of the first optimized code that removed the any to the last version of code that basically got rid of all the link statements in the code. What we can see is we now have, on top of the already existing gains, we have 5 to 64% throughput improvement, and we have a Gen 0 garbage collection reduction by 23 to 61%. That's amazing, right? But hold on a second. I told you we always should measure and we shouldn't assume. Let's have a closer look onto the data. When we look close, very close, we can see that in certain types of input parameters where we're getting lazy enumerated enumerables, that's a mouthful, we're actually 56% slower, right? So now the question is that an indication that we shouldn't be doing this refactoring? Well, it depends, right? So if you know what is going to be passed into the method, and in the SDK case, the team actually had telemetry, and we knew that it's mostly going to be concrete, non-lazy enumerated enumerables that we're getting. The decision was, in the Azure SDK case, we're going to do this optimization because we know that only in unit testing scenarios and whatnot, some other lazy enumerated cases are there. And we were willing to pay the price to actually do this optimization. But on the other hand, if you're knowing that in the majority of the time, you're getting lazy enumerated enumerables, then what you might want to say is that, well, we're just removing the link any, but then we stop there, right? So essentially what we're doing is we favor readability, and we use that as the key driver instead of trying to gold plate every part of the code in the code base. And there is likely some other areas in the code that are slowing things down even more. And in order to know that, fire up your favorite memory and performance profiler and get a better understanding of what's going on, and then optimize potentially the piece of code outside that area. But again, it's essentially a deliberate decision, and always asking yourself, are we done here? Can we do better? is it worth doing better, right? Make an experiment, measure it, and then look at the trade-offs and make the right trade-offs. And that might also be depending on essentially the knowledge of the team, whatever you're using, essentially a simpler version of the code, because it's not executed at tremendous scale or not yet executed at tremendous scale, right? So again, the context of the piece of code also includes knowledge of the team, how far you want to go, the input parameters, and all these things need to be taken into account in order to make reasonable trade-offs, essentially. I'm going to cover some of the questions a little bit later. I see there are a few questions in the chat. I'm going to cover them towards the end of the talk, but I will definitely come back to those. Cool. The next one is, we already touched a little bit on closure allocations in our link queue performance investigation, but this is going into even deeper into that territory. So be aware of closure allocations. So closures can occur anywhere where we have lambdas, action, function delegates, custom delegates, whatever, that are being invoked that access state from outside of the lambda. Now you might be thinking, oh, my head just exploded. What does that even mean? Well, I'm going to show you an example. And here is a retry method that is from the Azure NetServiceBus SDK. And what this retry method or run operation method actually does, whenever we call something to Azure Service Bus, it's possible that the server will essentially return the server is busy, right? And in such a case, we need to essentially throttle down. It's almost like a poly mechanism where we have the possibility to gradually slow down but execute the same operations multiple times until we succeed or until we actually reach a certain timeout that we have defined. And this is such a method. So what it does, it returns a task because we're going to call IO-bound operations, and then it accepts a func of time span and task as an operation. And then what it does, it essentially awaits this operation with the timeout, and it does it in a while loop. And if it was successful, it returns or it catches the exception, and then it retries. When the server is busy, it then essentially does a task delay and waits a little bit. Let's look closer at the usage of this run operation method. So if you use this retry policy run operation, what we can see is, as an example, when we're calling create message batch internal async, what we can see here is that we have a local variable that is on line 1. It's called message batch, right? And then we have the curly braces between line 3 and 6. And in there, we access this local message batch. So because we're accessing state that is outside these curly braces up there, right? We're accessing this message batch state, we're going to have a closure allocation whenever this method is called. And we can see that if we decompile this code. So when we decompile this code, what we can see is in the first few lines, we have a display class allocation. The display class allocation is there in order to hoist all the state that is necessary for that lambda to be executed. And then on line 8, we have a func of time span of task allocation that is also happening essentially to point to the right method. So we have two allocations in this piece of the code that are actually totally unnecessary. How can we change that? How can we optimize it? Well, we can optimize it by building sort of an infrastructure library thingy, and it's also called run operation, and we apply a few modernization techniques to make this code faster. So the first one to do is, well, there is this thing called value task. And for those who haven't heard of it, value task is basically a discriminated union out of a result or an IO-bound operation. It's very useful if you, for example, have cases where in the majority of the time you're getting an already cached value, or sometimes you're yielding to fetch something from the database, cache it, and return it back. Because then you save yourself a few allocations. Some people would argue that you should be using value task everywhere. That's where you have tasks. That's totally okay. Your mileage may vary. I just want to say I use it primarily in the cases where the majority of the calls are cached and only occasionally we're doing IO-bound operations. Here, because it's an infrastructure library piece, we decided to make this run operation return a value task. And then what we have to do is we have to essentially have a function delegate that accepts T1 as a state. So we have a function delegate that gets T1 as a state from the outside. We're using a generic time spent cancellation token, and it returns a valid task of T resolved. And then on line 3, what we're getting is T1, the actual state in, right? Why are we using generics? Well, and not object. Well, if we would be using object and if we pass in a value type, we would get boxing allocations, and those allocations are also expensive. So we want to avoid that. So we want to use the generics here in this specific example. And then what we do is we simply call the operation, pass in T1, the try timeout and the cancellation token, and then we are ready to go. So with this basic functionality or helper thing in place, what we can do is we can essentially now build on top of it. So what we're going to do is we have this run operation T1 method again, right, where we're essentially returning a valid task. So when we're not returning results, but we're using the helper method. Again, we also switch to valid task as here. Then we have the same input parameters. And then what we do is, essentially what we do is we're calling this run operation method, and we're passing on line 12 as a value tuple. We're passing the state and the operation, which is the function delegate in. And then inside the lambda, we deconstruct this state. It's on line 8. And then we have T1 and the operation. And then we can call the operation and pass the original state in. And as you might also have seen, we're also using the C#9 feature to mark a lambda as static. And what that is going to do is essentially gives us the possibility to safeguard sort of the closure so that we cannot access state that is outside of the closure, because the compiler enforces that for us. Okay, so like I said, this is the essential deconstruction, line 8, and this is the actual calling of it. Okay, and if we decompile this with this small change, small in quotes, right, we now have essentially, when we look at it, we have our beloved pattern essentially of this question mark assigning a static field, and now the delegate is statically cached and all the state is passed to it, and we have no closure allocations anymore. Now you might be asking yourself, but hey, how would I even discover these types of allocations? Well, what you can do is you can use your favorite memory profiler, and you can watch out for excessive allocations of the display class or various variants of action and function delegate allocations. Or you can use a more proactive approach. So for example, if you're coding with Rider from JetBrains, you can use the heap allocation viewer, or you can use in Visual Studio the heap allocation analyzer that proactively tells you in your code whether you have a closure allocation, and then you already know it while writing the code. And you might be thinking, well, but Daniel, come on, I don't have that complicated code. Well, as a matter of fact, for example, if you're using concurrent dictionary and there's this method add or update, get or add, right? These methods, they also accept a delegate, right? And many of these methods, like in the generic dictionary, if you use that and if you're not using the state-based overload, then you will also have a closure allocations. And essentially what the .NET team does, they add these state-based overloads, for example, to dictionary get or add concurrent dictionary get or add or get or update, and then add or update, and then you can use the same trickery and you get less allocations. But now, as a last piece of resort, you might be thinking, come on, I mean, seriously? All that sort of mind-boggling code just to get rid of 2 allocations, is it even worth it? Well, I want to show you something. I work for a company called Particular Software, and we are the makers of NServiceBus, which is a messaging framework middleware library that is fairly popular in the .NET space. And we have a lot of customers worldwide. And essentially in there is this pipeline engine, and what the pipeline engine does, it essentially calls the customer code whenever a message comes in from Azure NetServiceBus, RabbitMQ, and whatnot. And this has to be highly performant because we don't want NServiceBus to be essentially the culprit of the customer's code, right? And in there, I did closure allocation optimizations. And if you're interested to hear more about it, you can go to particular.net/blog/pipeline-and-closure-allocations to read more about the pipeline engine and whatnot. And I did these optimizations, and what I got out of it is I got a throughput improvement in a pure pipeline invocation of 74 to 78%, and all the allocations are gone. Well, as you can see, this is actually a pretty amazing technique that I applied in NServiceBus to get sort of a 5x throughput improvement just by getting rid of these essentially 2 allocations that I showed you before in the previous example. Okay, let's go to the next one. We're going to look into avoid excessive allocation to reduce GC overhead, pool and reuse buffers and larger objects. So in the Azure Service Bus SDK, there's this concept of lock tokens that I already told you about, and they're getting from the network. And in there was this code where we essentially had an array segment, and then we allocated a byte array of 16 bytes, and then we buffer block copied essentially the array, the GUID bytes into that array, and then we created a GUID. And this code is executed at scale, and if we can optimize it, we can actually win a ton of throughput. So what I did was I heard about this concept of the array pool, and I was like, oh, I can apply the array pool. And for those who haven't heard about array pool is basically almost like a car rental, right? You can go to the car rental and say, I want a 4-seater car. And the car rental might say, well, I can give you one that exactly fills your need, or we only have a 6-seater car available, but you can drive around. So what you get from the car rental is essentially a car that fits the amount of people you want to fit into that car. And that's the same for array pool. It just gives you arrays instead of cars, right? That's conceptually quite similar. And I started applying this array pool thing. So what I did, I rented an array of 16 bytes. And then I used buffer block copy to copy it into it. And at the end, I need to return the buffer back to the pool because I just rented something from the pool. So again, it's very important to measure and not just make assumptions whether this code is actually efficient or not. So let's have a quick look how we are doing. We're measuring this, and what we're getting is, as we can see, is we now have all the allocations are gone, but we are 226% slower than the previous code. Now the question is that bad? Well, the thing is, if you are in a memory constrained environment where you're willing to trade off throughput for less memory usage, this might be an optimization that you can do, right? That being said, we can actually do better. And we're coming now to the next rule. So for smaller local buffers, consider using the stack. And I'm going to use the same example. So here, so instead of essentially allocating 16 bytes every time we do buffer block copy, what we're going to do is we're going to use stack alloc of 16 bytes. I'm going to talk a little bit more about span a little bit later, but we allocate 16 bytes, and then what we do is we then use as span copy to, and we copy the memory into it. And the good thing is with stack allocation is whenever the method returns that has a stack alloc, the bytes will automatically cleared. So we're not paying essentially for a heap allocation. And you might be thinking, but Daniel, come on, why are you even copying the memory here, right? Because the GUID has a CTOR that essentially supports read-only span. Why can't you just pass in the array segment? That's a very good point. So essentially, in there, we're using Net Standard 2.0, and some of these GUID constructor overloads are not available. Plus, this is also a little bit of a simplified example to demonstrate stack alloc, because the actual production code is way more complex, but because it also essentially needs to deal with endianness and all those types of things. So I'm just demonstrating this here in a slightly simplified example. But if you're interested to see the actual production code, I can always point you in the right directions, right? And I'm also showing you this. In some cases, when memory copying is necessary, stack allocations is a pretty nifty way of essentially saving yourself some allocations. And again, let's benchmark how we're doing this. So what we can see is we now are 45% faster in terms of throughput, and all the allocations are gone, right? So again, for small small local buffers, consider using the stack and consider using the stack alloc keyword to essentially do that instead of using the array pool. And sometimes you actually need to combine both together. I'm going to show you that a little bit later. Be aware with stack allocation, never ever stack allocate something that is unbound or is controlled from the outside from a caller, because that can lead to really nasty problems, right? You can only stack allocate if you exactly know how much you are going to allocate, because if you stack allocate more than you have available space on the stack, then things are going to blow up horribly at runtime. Okay, cool. So let me quickly recap some of these rules. Avoid the excessive allocation to reduce GC overhead. We have the link queue optimizations. Be aware of closure allocations. Pool and reuse buffer. For small local buffers, consider using the stack. And I have 3 more. Be aware of parameter overloads. And where possible and feasible, use value types, but pay attention to unnecessary boxing. I talked a little bit about that. And the last one is also important, move allocations away from the hot path where possible. So sometimes what you can do is, if you control things, you can allocate on the heap a byte array, and then you reuse this byte array all over the place. That's also a pretty nifty technique. Let's go to the last but potentially most complex piece of this talk, which is avoid unnecessary copying of memory. So with C# 7.3, we got the span, right, that I already talked about, and span is excellent to avoid unnecessary copying of memory. And what span essentially is, it's a struct that has a pointer that points to a memory location, and it has a length that essentially determines how long the memory location is. And as you can imagine, it is almost like a curtain, right? You can essentially have a large memory, and then you can pull in a curtain, and you can say, I only want to see that much. I only want to see that much, whatever it is, right? And that's super cool. And it gives you the safety guarantees that you cannot read across essentially the boundaries of the span. There's also its cousin, it's called memory of T, which is there when you essentially have a heap allocated memory. By the way, it's a gross oversimplifications. There are actually talks that go into detail of span and memory of T, and the actual implementation, usage scenarios and where span lives and whatnot, they're way more complicated. But conceptually for this talk, I think it's a good enough representation to understand what a span is. And if you look at sort of the most important rules is, look out for stream and byte array usages that are copied or manipulated without using span or memory, and replace existing data manipulation methods with newer span or memory-based variants, right? So whenever you, and conceptually, it's actually just one rule, use the span or memory-based overloads of the things that you have in place, because that gives you tight control over what you're passing in. It's faster. It supports ways of pooling that we looked at, passing on stack allocated memory and whatever. So it's way better essentially in terms of usage than using, for example, byte array based overloads. But the problem is with these copying of memory, sometimes they're not really obvious to spot in the code base, and it requires a deep understanding of what's happening under the hoods of the framework and library that is in place. And in the EventOps SDK, there is this publisher type that uses internally a partition key resolver that turns essentially a string into a partition key. And that part of the code is used 30 to 40% on the hot path, the partition key algorithm, and it will be represented whenever users of the EventOps SDK of that specific publisher type are publishing messages to the EventOps. And it accounts for a non-trivial amount of CPU and memory cycles using that publisher type. I'm going to show you the first version of this partition key algorithm. And what we can see here is it's not really obvious where the allocations or the copying of memory is happening. But if you're looking closer, what we can see here, we have this encoding get bytes method. And if you look at the method signature on line 11, what we can see is we have a byte array that is passed to that method. So the method get bytes already kind of tells you get bytes means we're getting a byte. And because we're getting a byte from the runtime has to allocate a new byte array whenever we call it, because it doesn't know what we're going to do with that byte array, right? It's not in charge of essentially owning that memory. So it has to give it back to us in sort of a fresh version. And what this method is going to do, it takes a string and turns it into an UTF-8 encoded byte array, and then it passes it to this compute hash method. And now let's dive into how we can optimize this code. And now all the rules that we have talked about are sort of coming together. So what we can do is, first of all, we turn the string that we're getting, we turn it into a span because we want to use the span-based overloads. And then what we're going to do is we have to know approximately how many chars are there or how many bytes that we need to have. And there is this get byte count method. We're not going to use that because get byte count essentially needs to go through all. It gives us an exact byte representation, but we don't want to know that because this is way more efficient because it's O of 1. So we ask for an approximate representation of this, how long this partition key is. And then we apply the techniques. So what we're going to do is, if the string that we got is pretty small and it fits an arbitrary stack limit, we're going to stack allocate up to that stack limit. So we're essentially over-renting on the stack. Otherwise, we're going to get an array from the shared array pool for that specific length, and we're getting potentially more, right? But that doesn't matter, because we're then going to use the span-based overload of get bytes, where we can pass in the span, and we can pass in the buffer that we should just get. And what it will then write essentially the string into that buffer, right? And then what it's going to do, it returns us how many bytes it has written, the exact number of bytes. And we can use that then with the span to essentially draw in the curtain and slice the array. And then we know exactly how much we have written. And that's cool, right? Because we essentially over-rented. We have way more space than we actually need, but that doesn't really matter because we know exactly how much we have written, and we are then guaranteed to always be within those boundaries. Cool, and then at the end, we are essentially returning the shared buffer back to the pool. We're not using a try finally because we looked at the error cases, again, context of the piece of code, and we decided it doesn't require try finally because try finally would again blow up essentially the code size of this partition key algorithm, and that would also attribute to longer execution times. So we want to make sure that that is not happening. So we return it to the pool. And then the last thing, and then we pass the read-only span of bytes to the compute hash method. Otherwise, the compute hash method is exactly the same. And last but not least, it's on line 1, we're adding the skip locals init attribute. And what this attribute does, it essentially tells the compiler that it shouldn't clear the memory that we stack allocate. And then it's extremely fast because the majority of the time when we stack allocate on line 15, it's going to spend on essentially clearing that byte buffer. And we can actually tell it because we know exactly what we're going to write into. We might get garbage, but we overwrite garbage to the point where we have written, and then we draw in the curtains with the span slicing. So we are essentially sure we never get garbage in the reading. So we can apply this optimization technique. And now, after having applied all this, we can now measure, and what we can see is, compared to the original algorithm, we are now 38 to 47%, depending on the cases, faster in terms of throughput, and all the allocations are gone, which is pretty fantastic because previously it allocated essentially depending on the input size of the strings. Okay, so let's go. Let me skip this one. Let's wrap things up. Like I said, at scale, implementation details matter, but it's important that you do not apply these optimization techniques blindly everywhere, right? Always go and look for the expensive I/O path first. When you have database calls that take hundreds of milliseconds, then optimize those database queries because you get orders of magnitudes of more performance improvements when you tweak those first. And once you have done all the IO-bound optimization, query optimizations, whatnot, then you can start thinking about if it really matters and the code is executed at scale to apply the practices and principles that I have showed here today. And just to essentially give you a little bit of an oversight, what has happened with these optimizations. So all the contributions that I've done to the, for example, EventHubs SDK attributes to an 8% increase overall publishing throughput performance improvement, and likely a 3 to 4% performance improvement on the processor side. So you wouldn't want to have for free, essentially with just an SDK upgrade, 8% more throughput improvement in publishing and 3 to 8 in receiving, which is pretty awesome, right? So again, for us as engineers, it's important that we know what to ignore and knowing what to pay close attention to in the code base we're working in. And sometimes ignoring means also ignoring the performance optimization techniques I showed you here today in the code bases where it doesn't matter, and where it does, consistently apply them. I have here also a QR code where you can go to github.com/DanielMarbach/performance tricks in Azure SDK. I have a very thorough README there where you can read up all the things that I showed. Should something have been a little bit too fast, but of course you can also reach out to me on Twitter at @DanielMarbach, or send me an email to daniel.marbach@particular.net. And I think I'm also now going to answer a few questions, if I still have time. Is that okay?
Yes, that's completely fine.
Cool, cool. Okay, so the first one is, let me see. As you mentioned, wait with instantiated collection until really needed question. Would using var keywords be more helpful on an assignment? So no, essentially not, because what it means, if you wait instantiating collection, you have to declare a local variable, and then you essentially down the line in the code, you then assign it once you know it's going to be ready, right? So that means sometimes you cannot use var for these cases, because you have to define the concrete collection type that you're using up there in order for it to be instantiated and used in other places, right? Because the scope of the local needs to be wide enough so that it can actually be used. So I don't think var is really appropriate in these cases. And the other one is, if you want to join multiple tables in link, then what would be the effective method, using includes or using joins? Okay, I think this is a question related to entity framework. I'm not sure. So I'm not sure if it's relevant for this talk, but what we can say is, well, if it's related to entity framework, IO-based operations, then of course you need to take into account things like lazy loading, efficient querying, right? And then it's important that you actually look at what is link with entity framework generating, and then optimizing those queries. And that's where you get like orders of magnitudes performance improvements as well, right? There's another question, is shallow copy efficient? I'm not sure what that question relates to, so I'm going to skip that one. Should you want to clarify this question, feel free to reach out to me or even put it into the chat. The other one is, what packages and tools would you recommend to use for a local dev benchmark in production performance monitoring? Okay, that's a great question. So local benchmarking, I would highly recommend benchmark.net. It's amazing. It's a great library. It's very productive. You can execute against multiple permutations of things. You can inspect GC collection. You can also look at code sizes and whatnot. So that's really cool. I would use that. For production performance monitoring, I would recommend to use something like Application Insight, Datadog, OpenTelemetry, whatnot, to essentially have spans and traces that represent your method calls. You can also, in these tools, you can tap into sort of the runtime metrics. So for example, you can activate .NET event counters, performance counters, and then those tools will actually feed them into the dashboards of your tool, and then you can trace, for example, on a specific call, on a specific node in your cluster, wherever it's executed, how much memory was used, how many garbage collection pauses there were, and that helps you essentially to trace down what's going on in your code, and then apply sort of these optimization techniques over time. But yeah, these take time. And sometimes you only know what you're looking for once you have stared at the code for a while and you have seen the production data for a while. So you have to essentially develop sort of spider senses to look out in your specific code base where these things are happening. But hopefully I've given you a lot of good techniques that you can apply yourself in your code bases. Yeah. Is there any other question?
Not for now, but we asked Simran Kaur, I believe, about the shallow copying, and we already have an answer. They said, I meant if we are shallow copying, would it hold more memory? Is it
okay.
more clear now?
Well, the thing is, whenever you copy something, right, you need to have a destination to copy to, right? So, and as in my idea, shallow copying, maybe he means or the person means something else. But my idea, shallow copying versus deep copying is you basically only copy the data that you have, but you're not following the references and also copy all those references. So in that sense, shallow copying itself uses less memory, right? That's for a fact, because you're not traversing through all the references and you're not copying all the state that is associated with the references. But still, when you're copying, you need a destination to copy to, which means you need memory to copy into. And that means you will have allocations. Maybe the person has a specific usage scenario they're looking for. I'm also happy to, the person can reach out to me in my email, further explain the scenario in privacy, and I'm happy to sort of contribute more ideas to solve that specific problem the person has. Yep.
Yeah. Okay. Thank you so much for everything, for the thorough presentation. I see some compliments towards you. So if you would like to thank them, they're in the chat section of Community Live. Thank you so much for your time and for being with us. It's been a pleasure. Thank you.
Thank you. Bye-bye. Have a great rest of your day.
Have a great day.
Bye-bye.
Thank you. You too. Bye.